Today we're going to be looking at angular acceleration. Last time we looked at angular velocity. So that's just kind of how our angle changes over time. And we know that if we're going to have velocity, chances are we can also have acceleration. We can have a change in angular velocity. That's really all we're talking about here. The other thing we're going to talk about is just like with angular velocity, we also had a tangential velocity, kind of a if we're on something that's moving in a circle, depends upon how far we are from that center of rotation. We'll also determine kind of how fast we are going, kind of if we were to let go, or like if I'm spinning a yo-yo, if I let it go at a certain point, what speed is it going? So just like that, we're also going to have tangential acceleration. That's really tied to the angular acceleration. So starting off here, looking at the formula I have here, angular acceleration is represented by the Greek letter alpha. Um, Really, it's just measured in radians per second squared, just like, you know, translational acceleration is measured in meters per second squared. Uh, Same thing here. That's going to be equal to the change in angular velocity, or that delta omega, which is just fun to say, just the final angular velocity minus the initial angular velocity, divided by time, or the change in time, however it is you want to look at that. The other equation for tangential acceleration, which is still meters per second squared, to find that, we're just going to take the radius, or the distance from that center of rotation, times the angular acceleration. It's pretty easy. Keep in mind, we are still working with radians as opposed to degrees, just because that's a little bit easier for describing things moving in a circle. All right, so we have a question here. As the wind dies, a windmill that was rotating at 2.1 radians per second begins to slow down with a constant angular acceleration of negative 0.45 radians per second squared. How much time does it take for the windmill to come to a complete stop? All right, so in this case, they give us was rotating at 2.1 radians per second. So that's kind of our initial angular velocity is 2.1 radians per second. Make that 2 a little bit loopier. Okay. They want to know how much time does it take for the windmill to come to a complete stop. So that means our final angular velocity is 0 radians per second. They give us the angular acceleration. Let's see how well I can do my alpha there. That's not bad. Negative 0.45 radians per second squared. And they want to know how long will it take to come to a stop. So I'm looking for t. So really, I'm just working with this right here. So let's plug in what I know. Or let's start by getting t by itself. So if alpha equals change in that over time, multiply both sides by t, and then divide both sides by alpha. In this case, my t cancels t there, alpha cancels alpha. So my time is equal to the change in angular momentum over angular acceleration. All right, so for the change in angular acceleration, final minus initial, so I have 0 minus 2.1 radians per second, all over the angular acceleration, which we said was negative 0.45 radians per second squared. Really, if I just get rid of that 0 there, negative 2.1 radians per second over negative 0.45. Open up a calculator quick. Wait for it to load, which is unusual. I can't believe that's taken that long. All right, so let me get out a different calculator quick. Thank you for bearing with me here. I'm going to go ahead and cancel out of that. There we go. All right, so really my negatives are going to cancel out. So I've got 2.1 divided by 0.45 That's going to equal 4.67. Sounds good. Now, either I can know time is going to be measured in seconds here, or in this case, I've got radians per second divided by radians per second squared. Dividing is the same thing as multiplying by the reciprocal, so I've got radians per second times second squared over radians. Radians cancels radians. Seconds going to cancel out that, so I'm left with seconds there. 4.67 seconds. All right, pretty easy. So it would take 4.67 seconds to actually come to a complete stop. So let's ask a different question. If the windmill fans or if the windmill blades are 5 meters long, what is the tangential acceleration at the tips of the blades? All right, I do need that. Okay, so now we've got tangential acceleration is equal to radius times the angular acceleration. All right, so in this case, I want to know the tangential acceleration. That's just a regular A. That's what I'm looking for. The radius, we said the blades are 5 meters long, and we want to know at the tips of them. And we said that the angular velocity is negative, go back to the previous question, 0.45 radians per second squared. All right. So in this case, I just need to, if I'm looking for acceleration tangential, that's already by itself. Okay, radius we said was 5 meters. Take that times our angular, negative 0.45 radians per second. All right, and that's just the math we have to do. So if I come back over and go 5 times 0.45 negative 2.25. And this kind of acceleration is meters per second squared. So really, at the tips of those windmill blades and stuff, they would be experiencing a acceleration, tangential acceleration of negative 2.25 meters per second squared. So every second, their tangential velocity would decrease by that much. Really, that's just kind of looking at acceleration kind of in this circular motion. Next time, we're going to look at centripetal acceleration. We're still talking about things kind of moving in a circle, but we're going to look at just how much acceleration is occurring, not tangentially, but towards the middle of the curve path. So with that, good luck with the practice problems and have fun.